Okay, today I will continue with the with ideals. Okay, let's remember what's an ideal. So if we have a ring, if R is a ring, I is a non-empty subset of R, then I is an ideal if x minus y is in I and R times x, x times R in I for all x, y in I and for all R in R. So that was the definition of an ideal. Now, and we also remember if we have a function from a ring into another ring, and we have a natural ideal, namely the kernel of f, namely that's the x in R such that f of x is 0. So in another way of saying this is that's the inverse image of 0. So this is an ideal in R, and if we have an ideal, if I is an ideal in R, then we can form this set of left cosets x plus i's such that x is in R. So this is a ring, and the addition is x plus I plus y plus I is x plus y plus I, and the multiplication x plus y, x plus I times y plus I is x plus y plus I. So this, so therefore, so this with these two operations, R over I becomes a ring, and if R has 1, namely multiplicative unit 1, then 1 plus I is the identity. Assuming that I is not equal to R, is identity of R over I. So that okay. Now remember what's an integral domain. Ring R is integral domain. If it is commutative, with 1. Oops, let me write again. Commutative means multiplication is a commutative, and it has 1. And if R has no zero divisors, So that means, i.e., no zero divisors means x, y is equal to 0 implies that x is equal to 0 or y is equal to 0. So the basic example is integers. Integer is an integral domain, and we also say that if, for example, let me say one more thing, R is integral domain, is a field. If it is an integral domain, and if every non-zero element is a unit. So if every non-zero, so here is an exercise for you. So let if U is a unit, of course, R is a ring with identity. So let me write like this. Let R be a ring with 1. If U is unit, then U is not a zero divisor. So of course we assume that 1 is not equal to 0. Okay, that's the that's an exercise to you. Next, with this, the kernel gives you one-to-oneness. We can determine by looking at the kernel of a homomorphism, we can determine whether it is one-to-one or not. So here's a proposition. Let f R to S be a function, be a homomorphism, ring homomorphism. Then f is one-to-one if and only if kernel of f is 0. So here is a proof. So first, this way, suppose f is one-to-one. F is one-to-one. So remember, 0 of R is inside the kernel of f. The reason is that this is because f of 0 is 0, so that 0 is inside the kernel of f. In order to show that kernel of f is 0, we need to take an element from f, kernel of f, let x be in the kernel of f, inside R, of course, and show that x is equal to 0. And show x is equal to 0. For this, since x is in the kernel of f of x is 0, but on the other hand, f of 0 is also 0, so that f of x is equal to f of 0. Since f is one-to-one, x must be 0. So therefore, kernel of f only consists of the point 0. Conversely, suppose that kernel of f is 0. So let x and y be in f with f of x is equal to f of y. So that we need to show that x is equal to y. So from here, if you add the inverse of additive inverse of f of, let me write like this, f of x minus f of y is equal to f of y minus f of y, so that this is equal to 0, so that f of x minus y is also f of x minus y. On the other hand, this is equal to f of x minus f of y, because f is a homomorphism, and that's 0. So that means x, since x minus y is mapped to 0 by f, so that x minus y is in the kernel of f, namely f inverse of 0. So therefore, but this is 0, consists of only 0, so that x minus y must be 0. So it follows that x is equal to y. So therefore, f is one-to-one. So that we prove the proposition f is one-to-one if and only if kernel of f is 0. So here is another interesting properties of ring. So here is a proposition. So if every finite integral domain is a field. So we assume that R is, of course, R is with identity, computative ring with identity, and it has no zero divisors. Here's a proof. So since R is, so let R be finite. Name finite means it contains only finite number of elements, finite set. Let R be an finite integral domain. Finite integral domain. So that we can write R as A1, A2, AN. So one of them is 0, one of them is 1, one of these elements. So this is, and AI is not equal to AJ, for I is not equal to J. So let A be an element of R, so that A is one of those, one of these AIs. So if you multiply, if you multiply A by AI and AJ, if you multiply like this, so that this is, so from here, you may write, when you take AI minus A times AJ is equal to 0, or A times, factor out AI minus AJ is equal to 0. So remember, we only need to show that, here, we assume that A is not 0. A is not 0, so that, let A be a non-zero element, and we need to show that A is unit. Okay, so that every non-zero element is a unit, will be a unit, so that R will be an integral domain. R will be a field. Okay, since look at this last line, A times this product is 0, and also we know that this A is not 0, and R is an integral domain, so that it has no zero divisors. So this our integral domain has no zero divisors, so one of them must be 0. Since A is not 0, A minus AJ is equal to 0. So that means AI is equal to AJ. So namely, so A times AI and A times AJ can be, so therefore, i.e., let's write this way, if I is not equal to J, then A times AI is not equal to A times AJ. So therefore, this set A times A1, A times A2, A times AN. So these are all different elements. So there are n elements here, so that this must be equal to R. So this n elements, and is a subset of R, and R is R contains n elements. So this is precisely R. So since 1 is this in R, so 1 is some A times AK for some K. So that means A is a unit. So that every non-zero element is a unit. Every non-zero element of R is a unit. So therefore, R is a field. So this is a nice problem. Every non-zero element is a unit. Oh, one more thing is that to mention is this lemma that we may use. So let R be an integral domain. And A is equal to AX is equal to AY, and AX is equal to AY. And integral domain, and A is a non-zero element. So if AX is equal to AY, then x is equal to y. So we can cancel a's non-zero elements from both sides in an integral domain. Okay, why is that? Here is a simple proof. So instead of using that it has no zero divisors every time, so we can just cancel a's non-zero elements from both sides, just like in integers. So here's a proof. Ax, if ax is equal to ay, this implies that ax minus ay is equal to 0. So, or a times x minus y is equal to 0. And since a is not 0, and R has no zero divisors, so that means this x minus y must be 0. So therefore x is equal to y. Namely, you can cancel, i.e., you may cancel a's from ax is equal to ay in an integral domain. Nice. Next. Okay, so here's a definition. Maximal ideal now. Maximal ideal and simple ring. So here is the definition. Let R be a ring and let I be an ideal of R if the only ideals of R are 0 and R itself, then it is called as R is called a simple ring. So simple group means it has only only normal subgroups are trivial groups, and the group itself it is just like that, this definition. Ideals corresponds to normal subgroups. And second, this I is called if I is not equal to R, sorry, and if for an ideal J with I is inside J, that's inside R. This implies that if this implies that I is equal to J or J is equal to R, then this I is called the maximal ideal. So maximal ideal is simple ring. Maximal ideal is an important concept. So remember, in a field, there is no only ideals are 0 and field itself. So not an example, if R is field, then it is simple. And so here is an example I urge you to do. So if you take R to be integers and P prime number, if P is a prime number, then P times Z is an ideal, and I ask you to show that this P of Z is a maximal ideal. The maximal ideal. So namely, you will show that. So if we have an ideal in J in Z with this property, then either J is equal to P times Z or J is equal to Z. So remember, P times Z is P times N such that N is in Z, so that it is 0 plus minus P plus minus 2P, etc. So this multiples of P. Okay, the maximal ideal. Next is that here's a proposition. Let R be a ring with 1. With 1. And I be an ideal of R. I be an ideal of R with different than I, proper ideal. Then there's a maximal ideal. There is a maximal ideal. M of R such that this M contains I. So every ideal is contained in a maximal ideal. Okay. So here's a proof. Proof uses Zone's lemma. Okay. Let's define a set S like this. Namely, these are the J's such that J is an ideal of R. An ideal of R. And J contains I, and J is not equal to R. So that, look at this set. Look at that set. So since I is an ideal of R, it is inside R, and I is not equal to R. So by the very definition of S, this I is an element of S. So that S is not empty. This is not empty. So let's define for J1 and J2 in S. Let's define like this. J1 is less than or equal to J2 if and only if J1 is a subset of J2. So with this relation, this S with this less than or equal to is a partially ordered set, and let C be a chain in S. So a chain means any two elements can be compared, right? So so it's an increasing order. So let J be the union of all L's in C. So then J is an ideal. Ideal of R. The reason is that if X and Y are in J, so that X is in, let's say, some L1 in C, and Y is in L2 in C. C is like this, C. So since L1 is equal to less than equal to L2, or L2 is less than equal to L1, one of them. Let's assume that L1 is less than equal to L2, so that X and Y are both in L2, so that X minus Y is in L2. Hence, X minus Y is in the union of those L's, so that it's in J. And okay, that's the first condition satisfied. So we are showing that this is J is an ideal. J is an ideal. And so here L1 is less than or equal to L2, or L2 is less than or equal to L1. And without loss of generality, assume that L1 is less than or equal to L2, so that, and you proceed like that. Now, let X be in L, J, sorry, and R is in R, so that J is in the union, so that J is in, the X is in L for some L in C. Since L is an ideal, R times X and X times R in L, since L is an ideal, so that R times X and X times R are in the union of those L, so that it's in J. So therefore, we prove that J is an ideal. J is an ideal since I is inside J, I is inside J, and each and one of them is not in L for every L in C, for every L in C. So therefore, the reason, because L is not equal to R, so that they don't contain union, so that one is not in the element of the union of all elements in C, so that that's the J. Strictly speaking, I should write like this. L such that L is in C, so that that's equal to J. So therefore, J is the proper ideal of R. And for any L in C, so if you take any element in LC, then L is less than is inside J, so that L is less than or equal to J. So that means J is an upper bound for the chain C. So namely, every chain has a upper bound by Zorn's lemma, so i.e. every chain C in S has an upper bound by Zorn's lemma. This S has a maximal element. Has a maximal element. Okay. It has a maximal element. M, maximal element, let's say M. So M is in S implies that I contains M I is contained in M, and M is not equal to R, and M is an ideal. And assume that, so it's a maximal element of S, and we will show that claim that it's a maximal element in S, but we claim that M is a maximal ideal. Maximal ideal of R. So assume that. Assume M is not maximal ideal. So that there is an ideal. There is an ideal K between M and R. So in this, so since K is not equal to R and I is inside K, so that means K is in S, and M is less than or equal to K, and M is not equal to K. M is not equal to K, and this contradicts the maximality of M in S. Remember, M is a maximal element, not the maximal ideal. In S, M is a maximal element in S. So that so we show that if M is not a maximal ideal, then it cannot be a maximal element. So therefore, M must be is a maximal ideal. And also I is contained in M. Okay, that's the end of the proof. By using Zorn's lemma, we showed that every ideal is contained in a maximal ideal. So ideal I is contained in the maximal ideal M. Okay, next. Next, here's a proposition now. Let R be a commutative ring. Commutative ring with one. And let I not equal to R be an ideal. Ideal of R. Then I is a maximal ideal. If and only if R over I is a field. So there might be various proof of this statement, and I will just show it directly. So let I be a maximal ideal. I be a maximal ideal. So since R is commutative ring with one, implies that this R over I is commutative with one, and the one of this ideal R over I is, remember, 1 plus I. Okay, and let's show that every element of, we need to show that every element of R over I is every non-zero element. Not every non-zero element of R over I is unit. So remember, zero element of R over I is I, just I itself, or 0 plus I, if you like. That's the 0 element. And identity is identity is 1 plus I. Okay, so let U plus I be R over I be a non-zero element. So that U plus I is not equal to I. So that means U is not I, is not in I. Okay, let's consider this. Remember, we can look at the sum of two ideals, the ideal generated by U and I. This is X plus RU such that U is constant, U is in R, and X is in, so where X is in I, R is in R. So this is an ideal of R. So you can check this also. And if you look at U, we can write U as 0 plus 1 times U. This is in I plus U, I plus U, but it is not in I. So there, since I is maximal, so I plus U must be equal to R, right? I plus U is equal to R, so that 1 is in 1 plus U, so that we can write 1 as X plus U times V for some X is in I, V is in R. So some V is in R. So in this case, so that 1 plus R is equal to the left cosine of this X UV, plus I. So this is equal to X plus I plus U plus I times V plus I. But this is 0, namely 0 plus I, so that if we can forget about this, it is 0 of R over I. So that this is left quotient of U times left quotient of P is the multiplicative identity of R over I. So therefore, U plus I is a unit in R over I. So thus, R over I is a field. So it's a competitive ring with 1. Every non-zero element has a inverse. Yes. Every non-zero element in R over I is a unit. Next, conversely, suppose that R over I is a field. Suppose R over I is a field, and we will show that I is a maximal ideal. So let J be an ideal of R with containing I and inside R. We will show that J is equal to I or J is equal to R. Assume that, okay. So let's look at, so assume that I is not equal to J. So that then J over I is an ideal. You may check this. It's an ideal of R over I. and j over I is not 0 plus I. So since R over I is a field, and only ideal of R over I is a non-zero, and its group ring itself, the field itself, so that J over I is equal to R over I. And here's an exercise for you. Show that it follows that J is equal to R. So i.e. I is maximal ideal. So that's the end of the proof.